Hello everyone. This is lecture 5 of 124104 Physics 1A. In this lecture, we will learn about the laws of motion. First, we will define what force is. Then we will identify forces that we will commonly encounter in physical scenarios. From there, we will then define Newton's three laws of motion. And we will see that the second law of motion allows us to calculate the acceleration due to a force on an object. So what we have learned so far since the beginning of the course, we have been talking about kinematics. Just a refresher, kinematics is all about describing an object's motion. So we started this course by talking about what distance, displacement, velocity, speed, and acceleration are. So those physical kinematic variables describe an object's movement. We then looked at the motion of an object in one dimension, like horizontal motion on a straight line and vertical motion, looking at free fall as an example. We then moved on to describe the motion of an object in two dimensions, and we use projectile motion and relative velocities to as examples of motion in two dimension. So we have learned how to describe an object that is moving, but why do objects move in the first place? What causes an object to accelerate? So these questions are what we will answer in this lecture. Specifically, we will talk about the connection between force and motion. When we connect force and motion, this is a branch of mechanics called dynamics. So in this lecture, we will focus more on defining what force is, describing Newton's three laws of motion that govern the effect of exerting a force on an object. And then we will identify different types of forces. For example, weight, friction, and tension. And these forces are acting on an object that could produce acceleration for the object. In our next lecture, we will then apply what we learned about force and Newton's laws in solving problems. All right, so let's begin by defining what force is. Force is defined as a push or pull on an object. So the figures here sort of show you examples of forces exerted on an object, right? If you push on this cart, then we say that we are exerting a force on this cart. Or if we pull this crate, then we say that we are exerting a force on this crate. Force is a vector quantity. Okay? And as we've learned before, a vector quantity contains both magnitude or size and direction. So it's important to specify in which direction you're pushing or pulling an object, because of course the object's movement or motion depends on the direction of the push or the pull. If you pull to the right, then naturally the object will move to the right if you pull with enough force. The unit for force is called the Newton, capital N. The Newton is a derived unit. It consists of the base units kilograms times meters divided by seconds squared. The Newton is defined as the force needed to accelerate a 1 kilogram object by an acceleration of 1 meter per second squared. So as you can imagine, and maybe by looking at these pictures here, given a single object, there could be multiple forces being exerted on that object. So the key here is to identify what are the forces being exerted on an object. So we will next learn about the different kinds of forces that an object could experience when it's made to accelerate. So this table summarizes the forces that we will encounter in this course. You have weight, normal force, friction, tension, elastic force, and thrust. In the second column gives you the symbols that are commonly used to represent these different kinds of forces. And force, as I said, is a vector quantity, so we should specify the direction. For some forces, the direction is very specific. For example, weight force being the force due to gravity, it's therefore always directed downwards towards the center of the earth. So the third column gives us the directions of the specific forces given in the first column. Some forces have an equation associated with it, meaning we can calculate that force given some physical quantity of the object. For example, again, weight force is defined as the force exerted by gravity on an object, and the weight force is calculated as the mass of the object times gravitational acceleration. So we will go through each of these forces in a bit more detail, but this table would be a good resource for you to go back to whenever you would like to you to remember the different kinds of forces, their symbols, directions, and associated equations. Okay, so let's start with the weight force, W or F subscript G. The weight force, as I have been mentioning, is the force exerted by gravity, and it is exerted on any object that has mass. So any object that has mass will always experience a gravitational force, right? As long as it's in a space where gravity exists, like on the surface of the earth where there's gravitational pull, then any object that has mass will experience the weight force. G, of course, here is what we have encountered before as the gravitational acceleration, 9.8 meters per second squared. So because gravitational acceleration or gravity always pulls on the object downwards, the direction of the weight force is also always directed downwards. Okay. Just a clarification here. Weight, when we say weight, weight is the force that the object experiences because of gravity. Weight is not the same as mass. Okay? So be conscious of that. In physics, when we say mass, mass is measured in kilograms. It's the amount of substance that the object consists of, whereas weight is measured in newtons, because weight is a kind of force. It's the force exerted by gravity on a mass. Right, so mass, it's independent of position because, as I've said, mass measures the amount of matter that makes up the object. So regardless of where the object is located at, whether it's on the earth or on the surface of the moon, if there are, say, 1,000 atoms making up this object, it will always be 1,000 atoms on Earth as well as on the moon. So mass is independent of position. Mass is also a scalar quantity, which we measure in kilograms. Um, yeah. Mass is a measure of the object's inertia. When we say inertia, it's the resistance to the change in its state of motion. The more mass the object has, the harder it is to move, and therefore the more force is needed to move it. Say, for example, you have this elephant with a big mass compared to the cart of kittens or cats, which has a smaller mass. The bigger the mass, the more force you need in order to move the elephant, but the smaller the mass, the less force is needed to move those cats. Right. So let's look at this example to further distinguish between weight and mass. An astronaut's mass is 70 kilograms. What is the astronaut's weight force on the Earth and on the Moon? The gravitational acceleration of the Earth is given, and the gravitational acceleration of the Moon is also given. So on the surface of the Moon, the gravitational acceleration is bigger compared to the gravitational acceleration on the surface of the Moon, or rather, the gravitational acceleration on the surface of the Earth is bigger compared to the gravitational acceleration on the surface of the Moon. So if we want to calculate the weight force on Earth, that's defined as mass times gravitational acceleration on Earth. The mass is 70 kilograms, gravitational acceleration is 9.8, giving us a weight force of 690 newtons. If the astronaut goes to the surface of the Moon, the weight force is still calculated as the mass of the astronaut times gravitational acceleration, but this time we use the gravitational acceleration on the surface of the Moon. The mass is always the same regardless of where the astronaut is. So the mass of the astronaut will still be 70 kilograms on the surface of the Moon. Gravitational acceleration will be smaller, and therefore the weight force experienced by the astronaut on the Moon will be smaller compared to what he or she experiences on the surface of the Earth. Okay. So this example illustrates what I have been emphasizing, that the mass is always the same regardless of where the object is, but the weight force changes depending on position, because the gravitational acceleration could change for different positions or locations. Right, the second kind of force is called the normal force or support force, and we use the symbol N or F subscript N to designate normal or support force. Support force is the force that a surface exerts on an object with which it is in contact with. And that's why it's sort of intuitive to call it the support force, because you have a physical surface that is supporting the object, right? So in this illustration, in these figures here, you have here the inclined plane that's supporting a box, or the desk, the surface of the desk that's supporting this object here. The support force is always perpendicular to the surface. Okay? It's easy to see if the object is on a flat horizontal surface, then we can easily see that the normal force is perpendicular to the surface that's supporting it. But even if the surface is inclined or tilted at an angle as shown by this inclined plane here, the normal force or support force is always also drawn perpendicular or it's always perpendicular to the surface that's supporting the object. The Latin word for perpendicular is norma, and that's why the support force is also called the normal force. Okay, so that's where normal, the word normal, comes from. It's from the Latin word norma, which means perpendicular. Okay. I would also emphasize, because I see this often as a misconception among students. So say, for example, that's the ceiling there, and there's a string, and at the end of the string you have an object that's hanging at the end of the string. Um, a common misconception is to think that the string provides a normal or support force on the object because, well, intuitively, oops. Intuitively, you can see that you can argue that the string is supporting the object and therefore the object does not fall down. But the really key for identifying the support force is that there should be a physical surface that's literally in contact with the object. And this physical surface in contact with the object is the one that's supporting the object. So in this case, you have the object is supported by the string, but the string is sort of pulling the object upwards. If you put right, a flat surface below the object like so, right, then in this case, right, if the object is in contact with this flat surface, then this flat surface exerts a normal force. A normal force on the object that is perpendicular to the supporting surface, right? So just keep in mind that to identify a support or normal force, there should be a physical object that is in contact, direct contact with the object, and it is this physical surface that is supporting the object. The next force is called the frictional force. It's the force that resists the relative motion of an object, of objects that are in contact with each other. Frictional force is a result of, as you can see in this figure here, frictional force is a result of the microscopic irregularities of the surface, right? So if you can see this magnified view of the two surfaces here, the roughness of the surface is of the two surfaces is what provides the frictional force. And as the objects try to slide across each other, these irregularities will oppose the motion. So frictional force always resists the relative motion of the object. It is always parallel to the surface, okay? Right, so for example, you have this person in this figure pushing the cart to the left. The frictional force will be parallel to the ground, and it will always be, and it's in the opposite direction of the applied force. Okay. Right, so it's in opposite direction to the applied force because frictional force opposes the motion of the object. Okay. There are two kinds of frictional forces: static friction and kinetic friction. The type of friction depends on whether the object has started to move, in which case when the object has started to move, we call the friction kinetic friction, right? And sometimes when you're pushing an object, if you don't exert enough force, then the object will not move even though you're pushing it. the kind of friction in that case is called the static friction. So static friction is when the object is not moving. Once the object has started to move, static friction becomes kinetic friction. Right. You have here two equations that describe frictional forces. Frictional force given by the symbol small f is related to the normal force that we've seen earlier, Fn, as well as to some coefficient called the coefficient of friction. If, of course, if the friction is static, then the coefficient is called coefficient of static friction. If the friction is kinetic, then the coefficient is called coefficient of kinetic friction. So the coefficient of friction is sort of a constant number that describes how rough the surface is. So the more rough the surface is, the higher the coefficient of friction is, and therefore the bigger the frictional force the object experiences. Right, so this is a very useful relationship to remember. Frictional force is related to the normal force via the coefficient of friction mu. So this is the Greek symbol which we read as mu. Okay, it's like a fancy U, but we call it mu, representing the coefficient of friction. Right. Next force is called the tension force, F subscript T or T. A tension force is the pulling force exerted by a string, rope, cable, chain, or other non-elastic or non-elastic object. Right. So this is sort of, the example I used here with this illustration with the object hanging on the string. I've mentioned that if the object is just hanging by a string, we don't call it support force, although the string is providing the support on the object. The normal force is not present here. Instead, the kind of force being exerted on the object is called the tension force. So as long as you have a string, a rope, a cable, a chain, or other non-elastic object that is pulling on another object, then you should have tension or tension force. The tension force is always pointing away from the object. So in this illustration here, you have the bulb, which is the object. The bulb is connected to this wire or this cable. The tension force is therefore directed away from the object, and that's why the tension force is pointing upwards. Okay. Of course, the bulb has some mass, and as we've mentioned, any object that has mass will experience a weight force, and therefore you have this weight force that's directed downward as well. Okay, so for you to have tension force, the key here is that whatever is pulling on the object should be non-elastic, right? Or it's not easily stretchable. Once it's elastic or stretchable, then the kind of force that the object experiences will then be called the elastic or restoring force. Okay? Elastic or restoring force, F subscript L, EL, is the force due to a spring or other elastic objects like a rubber band or any elastic object. So let's look at this illustration here. You have a spring. It's originally unstretched. If you hang a mass at the end of the string, of course, we know weight force will pull on this mass downwards, and that causes the spring to be stretched. Okay. The elastic force has the tendency to try to restore the spring to its original unstretched position. So in this case, the elastic force would be directed upwards, as you can see in this illustration here, because the elastic force will try to restore this stretched spring to the original unstretched position of the spring. Okay, so because of this opposition, you can see here in this equation for the elastic force a negative sign. The negative sign means that the elastic force and the amount of stretch or the extension of the spring have opposite directions. Okay. So like looking at this figure again, the unstretched spring is stretched in the downward direction because of gravitational pull, and therefore the elastic force should be upwards opposite the direction of the stretch. And it makes sense because the elastic force will also try to bring back the spring to its original unstretched position. Right, so those are the different kinds of forces that I've shown in the summary table earlier, which we have defined each of them. Now, sometimes an object can experience two or more forces, right? As for example, in this illustration here, you have a weight force and a tension force acting on the object. And whenever we are analyzing forces, it's also useful to visualize the forces that are acting on an object. And so to visualize the different forces acting on an object, we draw what we call a free body diagram, or FBD. Free body diagrams are used to show the relative magnitude and direction of all the forces acting on an object, free of its surroundings, meaning we are just looking at an object and identifying what are the different forces acting on this object and drawing them in a free body diagram. Okay, so force is a vector quantity, so we use arrows to represent the force. The size of the force, or how big the force is being exerted, should be represented by the length of the arrow, and the direction of the force should be represented by the direction of the arrowhead that you draw. When you're drawing a free body diagram, because you are putting different kinds of forces, you should label the arrows that you draw with the exact type of force, because so then you will know which forces are acting on an object. It will also be useful to ask yourself the following questions. Is there gravity? Is the object located in a position where gravity pulls on that object? If the answer is yes, then you should draw a weight force or gravitational force. Is the object in contact with a surface, and is that surface supporting this object? If the answer is yes, then you should draw a normal force, because the normal force will be there supporting the object. Is there friction, meaning did it state in the problem that the surfaces are rough? Or that the friction is not negligible. Okay, so if there is friction, you should draw a frictional force, label that force as F. Is the object tied to a string, rope, or cable? If it is, then you should draw a tension force acting on the object. And finally, are there any applied forces? Meaning, does the problem say that the object is being pushed or pulled? In that case, we label the force as applied force. Right, so let's look at this example of how to draw a free body diagram. A car is being towed using a rope along a level ground, causing it to accelerate to the right. Okay. Consider frictional forces. So the problem specifically states that there are frictional forces between the car's tires and the ground. Maybe the ground is rough, like the car is driving on gravel or a rough surface, but it says that you neglect air resistance. Okay? Diagram the forces acting on the car. Okay. So you sort of go through this checklist and ask yourselves some questions. The easiest force that will always be present as long as the object is on the surface of the earth and the object has mass will be weight force, right? So there will usually always be some kind of weight force. Weight force is always directed downwards because gravitational pull is downwards. The car is along a level ground, so there is the ground. The surface of the ground that is in direct contact with the car. Therefore, there should be a normal force acting on the car. The normal force is always perpendicular to the surface, so it's upwards because it's supporting the car by exerting this upward force. Right. The car is being towed to the right. Okay, so there is some string or a cable that is used to tow the car to the right, and therefore you should have a tension force that is directed to the right. Okay, and the problem specifically says that there are frictional forces. Friction is always opposite the direction of motion, so the frictional force should be to the left, opposite the direction of the tension force that pulls the car to the right. Right, so this is the free body diagram for the car, right? We just consider the car independent of its surroundings, meaning you don't consider this youth. And you just draw the forces acting on the car, which is the object of interest. Okay. Right. Notice how each of the arrows are labeled with a kind of force. The directions of the forces are correctly indicated by the arrowheads, and if you can, but this is if you can collect the information about the relative sizes of the forces, then you should draw your arrows with the appropriate relative lengths. All right, so why do we want to draw the free body diagram? What's the purpose of visualizing all of these forces? The main purpose of drawing the free body diagram is it aids us to see the different forces acting on an object, and therefore it helps us calculate the net force acting on the object. Okay? When we say net force, it's the combination of all the forces acting on the object. And why do we want to find the net force? We want to find the net force because the net force determines the object's acceleration. Okay? If the net force right, if the net force is in the rightward direction, then you know that the object will accelerate to the right. Or here's an example shown here. If you pull on a box with 10 Newton force, as you can see in this figure here, and a friend pulls the same box oppositely with a 5 Newton force, right? We know that you have these two forces. They're both along the horizontal and they are in opposite directions. So in the last lecture, we learned that if the forces are in opposite directions, you sort of subtract these two forces. The force on the directed to the left will be negative. Hence, 10 minus 5 gives you a net force of 5 newtons. The direction of the net force follows the direction of the bigger force, right? So the net force is 5 newtons in the direction you are pulling the box. Since the net force is to the right towards you, the effect is therefore for the box to move to the right towards you as well. Right, so this sort of illustrates, firstly, why we want to draw the free body diagram. We want to visualize all the forces acting on the objects. Once we know all the forces, we can then combine the forces to find the net force. And once you find the net force, you can then find the acceleration of the object. Okay. So going back to the example of the car being towed, and the free body diagram that we drew earlier, assuming that we've the size of the arrows here drawn correctly to represent the magnitude or size of the individual forces, we can see that the rightward tension force is bigger than the leftward frictional force, right? So therefore, the net force along the horizontal axis or x-axis will effectively be pointing to the right, because the rightward tension force is bigger than the leftward frictional force. And then so effectively, since the net force will be to the right, the car will then accelerate to the right. Right? So just a quick reminder that force is a vector. The direction is important. We draw the arrow such that the length represents the size of the force, and the arrowhead or the direction of the arrow represents the direction of the force. And don't forget the convention that we are using for positive and negative directions. Right, just a little bit of quick check before we proceed. You have these two scenarios here. We want to find the net force in each scenario. So in the first one, you have two forces, 5 newtons each, being exerted in the same direction on this object here. Right? We know that, and in the second scenario, you have also these two forces, both 5 Newton each, but this time those two forces are directed in opposite directions. Right? So we've learned that if the two forces or two vectors are pointing in the same direction, we sort of add the two vectors together, and hence in the first scenario you have a net force of 10 newtons. The direction, of course, follows the direction of those two forces you've added. Whereas in the second scenario, you have two forces that are in opposite direction, and we learned that if the vectors are pointing in opposite directions, you sort of subtract these vectors because one of them will be negative, the one pointing to the left. So effectively, the net force in the second scenario is 0 newtons. All right, so we have so far identified the different forces that can act on an object. We defined each of them. We then learned how to draw a free body diagram, and then we sort of had a revision about how to get the net force. So why do we want to get the net force? As I've mentioned, the net force will determine the object's acceleration. Newton's laws of motion sort of describes the connection between the forces that act on the object and the object's movement. So in other words, Newton's laws of motion connects the net force to the acceleration. And there are 3 laws of motion. law of inertia, law of acceleration, and law of interaction. So let's go to each of these laws of motion, starting with the first law of motion, which states that an object at rest stays at rest and an object in motion stays in motion. When we say it stays in motion, it will continue to move with the same speed and in the same direction as long as there is no net external force that's acting on it. Meaning, if the net horizontal force along the net horizontal force is zero and the net vertical force is zero, such that the overall net force is equal to zero, then the object will continue to do what it's initially doing. If the object has been moving to the right all along, okay, it will continue to move to the right if the net force is equal to zero. So here's a good example of illustration of the first law of motion, right? You have a car that's moving to the right. The car is abruptly stopped by this barrier, right? If the person is not wearing a seat belt, okay, and hence there is no external force that is stopping the motion of the object, Newton's first law of motion says that the object will continue, or the person will continue to move in the same direction and with the same speed, because there's no seat belt that's sort of exerting this external force on the person. And that's why the first law of motion is also called the law of inertia, because inertia is defined as the tendency of an object to resist changes in its motion. Right? So as illustrated here, the person will keep moving to the right with the same speed and of course the same direction, because it will resist the change in its motion. And especially if there's no external force acting on this person, it will just continue to move along. Right? And that's why wearing seat belts will keep us safe, because it sort of stops our motion. When the car is stopped abruptly, the seat belt is there to stop us from moving forward as we have been moving all along. Right? I guess this video here illustrates the first law of motion and car safety and seat belts quite well. So watch this video before we continue with our discussion.
In a crash, whatever your speed, the car stops, but everything inside keeps moving. It's the same inside your body. Even with the best protection, you're still vulnerable.
Right? Okay, the faster you go, the bigger the mess, because if you're moving at 100 kilometers per hour and the car stops abruptly, everything else that has no external force will keep going at 100 kilometers per hour. And that's Newton's first law of motion. Right? Okay, Newton's second law of motion states that the acceleration of an object is directly proportional to the net external force. And this is what we were talking about earlier, right? Why we wanted to find the net external force, because the net external force determines the object's acceleration. Newton's second law of motion sort of just gives us the relationship between the net force and the acceleration. So it says that if the net force is big, then this will result to a big acceleration, which makes sense because if you pull an object with a very strong force, the object will move quickly with a bigger acceleration, as opposed to when you exert a small net force. If you pull an object with a small net force, then the object will have a smaller acceleration. Newton's second law of motion also says that the acceleration is inversely proportional to the object's mass. Inversely proportional means that if one is big, the other is small. Which also makes sense because if the object is massive, if the object has a big mass, given the same amount of force, the object will have a smaller acceleration, right? If you try to push a car, okay, the car will sort of move only a little bit. If you exert the same amount of force on an object with a smaller mass, okay, exerting the same amount of force, then that object will have a bigger acceleration, right? So if you're trying to push a car with a very big mass, with a certain force F, maybe the car will move only a little bit, if not at all. If you exert the same amount of force on a bicycle, for example, which has a smaller mass, then of course the bicycle will have a bigger acceleration. So that's Newton's second law of motion. Okay. So don't forget that both force and acceleration are vectors. Okay. And therefore, the direction of acceleration is determined by the direction of the net force. Okay. And if we rearrange this equation so that we have net external force on one side, then we get what is the more popular form of Newton's second law of motion: net force is equal to mass times acceleration. Okay. So here's an example illustrating Newton's second law of motion, which we sort of already saw earlier when we were talking about net force. You have this girl being pulled in opposite directions. The girl has a mass of 30 kilograms. Okay, as we have seen earlier, two forces in opposite directions and the same amount of force will amount to a net force equal to 0 newtons. No net force means no acceleration. Therefore, the girl will just be stationary. Okay. On the other hand, if the girl is pulled to the right with a bigger force compared to the pull to the left, the net force will then be 3 newtons in the direction of the bigger force, or to the right. Okay, if you have a net force, it means that there will be some acceleration. You can calculate what the girl's acceleration will be by using Newton's second law of motion. Net force is equal to mass times acceleration, or acceleration equals net force, 3 newtons to the right, divided by the mass, 30 kilograms. That gives you an acceleration of 0.1 meters per second squared to the right, indicated by this plus sign here in the answer. Okay. A car pulls, another example, a car pulls a 500 kilogram trailer along a rough road, as we can see in this picture here. The car and the road apply a net force of 1,000 newtons on the trailer. Okay. Calculate the acceleration of the trailer. Right, so it says here the car and the road. We sort of drew the free body diagram of this scenario already earlier, with the car being towed by a ute, right? Except this time we replace the car with a trailer. So so the free body diagram is still sort of the same. You have a weight force that's downwards, you have the normal force that's upwards, you have the tension force that's pulling the trailer to the right, and you have the frictional force that opposes the motion or the pull. Hence the frictional force is to the left. We are looking only at the tension force and the frictional force. The problem here says that the car and the road apply a net force of 1,000 newtons. So we're already given the net force, meaning we're already given the combination of the tension force and frictional force, giving us the net force of 1,000 newtons on the trailer. And we want to calculate the acceleration of the trailer. Okay. Newton's second law of motion relates the acceleration to the net force. We rearrange that to isolate acceleration. The net force is given 1,000 newtons, and the mass of the trailer is 500 kilograms. Therefore, the trailer will move with an acceleration of 2 meters per second squared. Okay, in which direction? It will be in the direction of the pull, in the same direction as the car, because it's the car that's pulling the trailer. Right. So just a little bit of discussion about the gravitational force. Right? It's sort of different from the weight force that gravity exerts on an object. The gravitational force is the kind of force that's exerted by two objects that are close by, and therefore these two objects attract each other. The objects are represented by masses m1 and m2, and r is the distance between those two objects. G is just a constant number. Okay, so if we calculate for the gravitational acceleration near the surface of the Earth, we use Newton's second law of motion. Force is equal to mass times acceleration, where force is equal to this one, the gravitational force exerted by the pair of objects. Then effectively we have mass times acceleration is equal to g times the masses of the two objects divided by r squared. We can then rearrange this equation. M cancels on both sides, and therefore we have acceleration is equal to gravity, which is a constant number here, g. Gravity times the mass of the Earth divided by the radius of the Earth. And if you work out, this equation, g capital M over r squared, putting the value of g as this constant number, the value of capital M as the mass of the Earth, and r as the radius of the Earth, you will arrive at the gravitational acceleration g is equal to 9.8 meters per second squared. Right? So this g equals 9.8 meters per second squared actually is a consequence of Newton's second law of motion, as well as the gravitational force that two masses exert on each other, namely the mass of the Earth and the mass of the object on the surface of the Earth. Okay, the last law of motion is Newton's third law of motion. It's also called the law of interaction because it says that whenever one object exerts a force on a second object, the second object exerts an equal magnitude and opposite direction force on the first object. So there are two objects that are interacting with each other and exerting force on each other. That's why it's called the law of interaction. It's more commonly known, Newton's third law of motion is more commonly stated as, to every action, there is always an opposite direction and equal magnitude reaction. Right? So here is an example of Newton's third law of motion. It's actually what allows us to walk. Because when we walk, we sort of, our foot pushes on the ground, okay, to the left, and as a reaction to the push of our foot on the ground pushes on our foot, and the reaction force is always in the opposite direction as the action force. And if our foot pushes on the ground to the left, the ground then pushes on our foot to the right, right? With equal magnitude. Okay. Right. So in this case, the action is the foot pushing on the ground. The reaction is the ground pushing on our foot. Notice how you have the action and reaction. The magnitude is the same, but the directions are opposite. Okay, so it's there's a simple rule to identify action and reaction pairs or action and reaction forces. First, identify what are the two objects that are interacting, right? There will always be two objects involved in the interaction. The action is where the object A exerts a force on object B. The reaction is object B exerting a force on object A. So notice how, right, you sort of just exchange the order for which the order of the objects. In the action case, the object A exerts a force on object B. In the reaction case, notice how the order of the objects are flipped, such that object B exerts a force on object A. So let's look at this example here. Describe the other force in the following action-reaction pairs. So in the first case, the action is given. The action is that the baseball pushes the glove to the left, right? So this is the force of the ball on the glove that's to the left. Okay. What is the reaction force corresponding to this action force? The reaction force will be, right, just exchanging. You have these two objects that are interacting. The baseball and the glove are the two objects that are interacting. You just sort of reverse their order such that the glove pushes the baseball. That will be the reaction force. And notice how the direction is opposite to each other. So the reaction force will be the glove pushes the baseball to the right. In the second illustration here, you have three objects that are interacting. You have foot A, foot C, and ball B. Okay, if you have more than two objects interacting, you sort of divide the scenario so that you're looking at two objects at a time, like foot A and ball B, and then next look at foot C and ball B. So in the interaction, in interaction, there are only two objects that you're looking at at any instant of time. So for the action case, foot A pushes ball B to the right. The reaction should be ball B pushes foot A to the left. Okay. For the second action, foot C pushes ball B to the left. The reaction will be ball B pushes foot C to the right. Okay. Right? So this slide just gives you some reminders about action-reaction pairs. They never cancel each other. So this is probably one of the most important notes I'll emphasize. The action-reaction pairs never cancel each other because they act on different objects, right? Foot A acts on ball B, whereas the reaction in the reaction case, it's the object ball B that's acting on foot A, right? So they always act on different objects, so they never cancel each other, and therefore you do not include them in the free body diagram, okay? Because the free body diagram just looks at the force on a single object. So for example, your object is the foot A, then you're just looking at the force exerted by ball B on foot A, and you're not considering the force exerted by foot A on ball B. Okay. Right, so to wrap up this lecture and Newton's third law of motion, this video sort of is a good illustration of Newton's third law of motion. So watch this video before I summarize the lecture.
Welcome to the International Space Station. I'm NASA astronaut Mark Vande Hei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time, a force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. Got a basketball right here. It's going to be object 1. I'm the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass, so Joe, get into a ball. I'll do the same. I'm going to face you this way so that I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
All right. So that's Newton's third law of motion, and that wraps up our lecture 5 on the laws of motion, where we first defined what force is, and then we identified different kinds of forces. We then learned how to draw these forces acting on an object using a free body diagram, and we learned the three laws of motion that relate the net force to the acceleration of the object. So I'll end lecture 5 and see you next time in lecture 6.